Machine learning techniques. Audio Ready Script Module 1 Introduction. Hello everyone, and welcome to this Machine Learning Techniques course in the online B.SC program in Programming and Data Science. My name is Aaron Rajkumar, and I will be your instructor for this course. In this module, we begin with a very high-level introduction to machine learning. If you have already taken the prerequisite course on Machine Learning Foundations, you may already have a basic understanding of what machine learning is and the kinds of problems it addresses. However, to keep this course self-contained, we will briefly revisit the core ideas to set the stage for what follows. Let us begin with a simple question. Why study machine learning? One major reason is its widespread real-world application. Modern digital systems rely heavily on machine learning. Reports such as those from Forbes on digital transformation trends highlight areas like analytics, artificial intelligence, conversational AI, and autonomous systems. All of these depend, directly or indirectly, on machine learning techniques. This shows that machine learning is not just theoretical, it is deeply embedded in practical systems. Next, we can ask, how popular is machine learning today? If we look at search trends over the past decade, terms like machine learning, deep learning, and artificial intelligence have all shown a significant rise in interest, especially since around 2016. Deep learning is a subset of machine learning, while artificial intelligence is the broader field that originally aimed to simulate human intelligence in machines. Over time, machine learning has become the dominant practical approach, although artificial intelligence remains a broader umbrella term. Now, let us consider where machine learning is applied. A useful way to think about this is to compare it with human capabilities. If we want machines to learn, we can look at tasks humans perform naturally and try to replicate them. One major area is computer vision, which aims to give machines the ability to see. Humans can look at an image and recognize objects like trees, faces, or animals. Machine learning tries to replicate this ability to object recognition and image understanding. Another major area is speech processing. Humans can understand spoken language even when it is unclear, noisy, or varies between speakers. Machines attempt to do the same through speech recognition systems. Text data is another important area. Huge volumes of text are generated every day on the internet. Understanding meaning, extracting information, or recognizing handwritten text are all machine learning tasks. A more ambitious goal is understanding the human brain itself. The brain contains billions of interconnected neurons and produces intelligent behavior. While we are far from fully understanding it, machine learning is inspired by its structure. Beyond human sensory tasks, machine learning applies wherever large amounts of data exist. For example, in finance, machine learning is used to analyze stock markets and make predictions about price movements. In science and engineering, it is used in experiments involving biology, chemistry, and materials science. In sports analytics, it can be used to predict outcomes of matches based on historical data. In e-commerce, recommendation systems suggest products to users based on their past behavior and similar users' preferences. Now that we understand where machine learning is used, we can ask, what exactly is machine learning? To understand this, it helps to first define what machine learning is not. Machine learning is not simply writing a fixed algorithm that maps inputs to outputs. For example, a tax calculation system follows predefined rules. It does not learn, it simply executes instructions. Machine learning is also not memorization. If a system simply memorizes training examples, it may perform well only on those exact examples. It would fail on new, unseen data. True learning involves understanding patterns, not storing answers. Machine learning is sometimes mistaken for magic because of its impressive results. However, it is not magic. It is based on structured mathematical principles and algorithms. So what is the key ingredient that makes machine learning different from traditional programming? It is data. Machine learning algorithms learn patterns from data and use those patterns to make predictions or decisions on new data. The goal is not memorization, but generalization. Generalization means performing well on unseen data, not just the data used for training. In simple terms, machine learning is about learning from examples so that the system can handle new situations correctly. At its core, machine learning is not magic, it is mathematics. It relies on statistical and computational methods to extract patterns from data and make predictions. Now let us look at some concrete examples. A common example is spam detection in emails or messages. The system learns from examples of spam and non-spam messages and classifies new messages automatically. Another example is weather forecasting, where historical data like temperature, humidity, and pressure are used to predict rainfall. Recommendation systems are widely used in streaming platforms to suggest movies or shows based on user preferences. Social media platforms use machine learning to suggest friends or connections based on shared networks and behavior. Another example is audio processing, such as separating vocals from background instruments in music recordings. Image grouping is also a common application, where photos are automatically organized based on the people appearing in them. More advanced applications include robotics, where a robot learns to navigate an environment by interacting with it and receiving feedback. Finally, stock market prediction is another example, where systems learn from historical trends and continuously update their predictions based on outcomes. In summary, machine learning is about building systems that learn from data, recognize patterns, and improve performance on new, unseen situations. This concludes the introductory overview of the course. So now these are examples, but what I want to do is give a high-level view of the broader paradigms of machine learning and how these examples fit into them. There are three major paradigms. First is supervised learning, where in addition to the data, you also have some kind of supervision attached to it. For example, you might have many emails, but that alone is just raw data without meaning. Then a teacher or a labeler comes and marks some emails as spam and others as not spam. Now you have both the input data and the correct answers attached to it. The task becomes learning how to map input to these labels. So in this case, learning how to separate spam from non-spam. That is supervised learning, where every example comes with a known correct output. Second is unsupervised learning, where you're only given data points without any labels or answers. You are not told what is correct or incorrect. You are just asked to find structure in the data. For example, if you're given many images without any explanation, you might try to group them in different ways. You could group images that contain animals versus those that do not, or group them into cats and dogs, or group them by number of objects, or even by colour patterns like white animals versus brown animals. There's no single correct grouping, because different notions of similarity can exist. Once you decide what's similar means, you can then cluster the data accordingly. This process of discovering groups or structure from unlabeled data is unsupervised learning. Third is sequential learning. We will not go into depth on this in this course, but it is important to note exists. In sequential learning, you do not get all data at once. Instead, you make a decision, then you receive feedback, then you make another decision, and again receive feedback, and this continues over time. So learning happens step by step through interaction. The feedback acts as supervision, but it arrives after each action rather than being given upfront. Each of these three paradigms has subcategories. In supervised learning, one major type is classification, where outputs belong to a finite set of labels. For example, spam versus not spam is classification with two labels. Even digit recognition, where outputs are digits from 0 to 9, is still classification, just with multiple discrete labels. Another type is regression, where the output is not a category, but a continuous value. For example, predicting rainfall amount is regression because the output can be any real number, not a fixed label. There are also other forms like ranking, where instead of only predicting an outcome, you also order results. For example, recommending movies is not just about saying yes or no, but also about deciding which movies should appear first. Another is structured learning, where outputs have internal structure, such as trees or sequences, but we will not focus on these in this course. In unsupervised learning, one major topic is clustering, which is grouping similar items together without labels. Another is representation learning, which is about finding better ways to represent data. For example, an image is just pixels, but there may be better ways to represent it that make tasks like recognition easier. Sequential learning also has different forms depending on feedback. In one setting, called full information feedback, you get outcomes for all possible actions, not just the one you chose. This is used in online learning settings. In another setting, called partial feedback, you only see the result of the action you actually took. For example, a doctor chooses one treatment and only observes the outcome of that treatment, not the others. This is harder. This leads to multi-armed bandit problems. Another related area is reinforcement learning, where an agent learns by interacting with an environment, making actions in states, and receiving rewards over time. A typical example is a robot navigating a room by learning, which actions lead it closer to its goal. Now we can map earlier examples into these categories. Spam detection is supervised learning, specifically binary classification. Rainfall prediction is supervised learning, specifically regression. Movie recommendation often involves ranking or ordinal classification. Friend suggestion in social networks is a link prediction problem, which is a form of supervised learning on graphs. Voice and instrument separation is unsupervised learning because there are no labels telling which part of the signal is voice or instrument at each moment. Grouping pictures into similar sets is clustering, which is unsupervised learning. Robot navigation is reinforcement learning. Stock market prediction can be treated as online learning because feedback comes over time and decisions are updated sequentially. Finally, the key prerequisites for this course are linear algebra, probability, statistics, and basic calculus, with some optimization being useful. These are needed because machine learning involves structure, uncertainty, and optimization. Linear algebra helps represent structure, probability helps handle uncertainty, and optimization helps convert data into decisions. The overall goal of the course is to understand machine learning beyond just using it as a black box. It is about understanding how algorithms learn from data, how they generalize beyond memorization, and how they can be applied to real problems in a principled way.
Hello everyone. Welcome back. Today we begin the mathematical foundations of this course on machine learning techniques. As mentioned earlier, this course covers different areas of machine learning, including both supervised and unsupervised learning, along with algorithms for each. We start with unsupervised learning. More specifically, the first part of the course focuses on representation learning, which is a subcategory of unsupervised learning. So what is the goal of unsupervised learning? We are given a set of data points, and the goal is to understand something useful about them. This sounds vague, and that is intentional. It is broad because we still need to define three things clearly: what we mean by data points, what it means to understand them, and what useful actually means. The easiest part is defining data points. We think of data points as vectors in d-dimensional space. That means each data point is just a list of d-real numbers, often called features. For example, if we collect height, weight, and age from people, each person becomes a point in 3D space. Each coordinate corresponds to one feature. So data points are just vectors. Now the harder question: what does it mean to understand data? And what does it mean to understand it in a useful way? To answer this, we introduce a key idea that will guide much of the course. There is a famous idea by George Chaitin: comprehension is compression. Comprehension means understanding or learning. So the idea is this: if you can compress data well, you have understood it well. In other words, learning is compression. If you can take data and represent it in a shorter form, while keeping the important information, then you have captured structure in the data. This idea will appear repeatedly throughout the course, so it is useful to keep asking, where is the compression happening in any algorithm? Now let us make the unsupervised learning problem more precise. We are given n data points. Each data point is a vector in d-dimensional space. So we can think of the dataset as n vectors in Rd. The output we want is a compressed representation of this dataset. To understand what that means, consider a simple example. Suppose we have four 2D data points, 7, -14, 2.5, 5, 0.5, 1, and 0, 0. Now ask a simple question. How many real numbers do we need to store this dataset exactly? Naively, each point has 2 numbers, and there are 4 points, so we need 8 numbers. That works, and it preserves everything exactly. But now ask, can we do better? If we look carefully, we notice something important. In every point, the second coordinate is twice the first coordinate, so all points lie on a straight line. This means the data has structure. Instead of storing all 8 numbers, we can exploit the structure. We choose a representative direction, for example 1, 2. This captures the line. Then for each data point, we store only a single coefficient that tells us how far along the line the point lies. For example, -7, 2.5, 0.5, and 0 become coefficients. Now the dataset is stored using one representative vector plus one coefficient per data point. That reduces storage from 8 numbers to 6 numbers. Now this may not seem like a big gain, but scale it up. If there were 1 billion data points, we would go from storing 2 billion numbers to about 1 billion plus a small constant. That is a massive reduction. And importantly, we can still reconstruct the original dataset exactly. We simply multiply each coefficient by the representative vector, so the representation is lossless. Geometrically, all the points lie on a line, and the representative captures the direction of that line. Now an important observation, the choice of representative is not unique. Any non-zero vector along the same line works just as well. We can scale it or normalize it, and the reconstruction still works as long as we adjust coefficients accordingly. So representation is flexible. Now generalizing this idea, in d dimensions, naive storage requires d times n numbers. But with this compressed view, we store roughly d numbers for the representative and n numbers for coefficients. So instead of dir storage, we get roughly d plus n. That is the core idea of compression in structured data. However, this only works perfectly when all points lie exactly on a line. What happens when they do not? Suppose most points lie on a line, but one point is slightly off. Now exact reconstruction using one line is no longer possible. We have 2 choices. We can either increase the number of representatives, or we can accept approximation instead of exact reconstruction. If we increase representatives, storage increases, and we lose compression. So instead, we allow approximation. We replace the off-lying point with its closest projection onto the line. This projection is the point on the line that minimizes reconstruction error. So we ask, what is the best proxy for a point on a line? The answer is projection onto that line. Mathematically, we find the scalar c that minimizes the distance between the point and c times the direction vector. Solving this gives a formula where the optimal c depends on the dot product between the point and the direction vector, divided by the squared length of the direction vector. If we normalize the direction vector to unit length, this simplifies. Then the coefficient becomes just the dot product of the point with the direction vector. So the projection becomes clean and efficient. Putting everything together, we now have a powerful idea. Data can often be represented by a small number of directions, and each point is expressed as a combination of those directions. When the data lies perfectly on a line, compression is exact. When it does not, we approximate using projections. This idea forms the foundation of representation learning and many unsupervised learning algorithms.
Now, in the previous discussion, we assumed something important. We assumed that we already knew which points lie on a line and which point does not. Then we showed how to project the out-of-line point onto the line to get a proxy representation. But in practice, that assumption is unrealistic. Nobody tells us which points lie on a line, or which line even exists. In reality, we are just given a dataset, a collection of points. So now the problem becomes more fundamental. We not only need to find the projections, we also need to find the line itself. There are infinitely many possible lines. So the real question is, how do we find the correct one? We will now use a key idea. Since we know how to project points onto a line, we will use that mechanism to actually discover the best line. Let us make this goal precise. We want to develop a way to find a compressed representation of data when the data does not perfectly lie on a line. In fact, this is the realistic case. It is extremely rare for real-world data to lie perfectly on a single line. For example, consider a dataset of 100 people where we measure height and weight. If we plot these points, we may see a general trend. As height increases, weight tends to increase. We might try to fit a line through the data, but almost no points lie exactly on that line. So exact linear structure is not realistic. This means something important. Real-world data almost always requires approximation. We still want to represent data using a line, but we accept that the representation will not be perfect. Now suppose there are two candidate lines. One is the red line, and another is the blue line. Both allow us to compress data in a similar way. In both cases, we can project points onto the line, store coefficients, and reconstruct approximations. So both give similar compression. But they are not equally good. Why? The difference is reconstruction error. If we reconstruct the dataset using the red line, the reconstructed points are closer to the original data. If we use the blue line, the reconstruction error is larger. So the better line is the one that minimizes reconstruction error, not the one that gives more compression. This leads us to a precise objective. Given a dataset, we want to find the line that minimizes reconstruction error. Now let us formalize this idea in words. We are given a dataset consisting of n data points, where each data point lies in d-dimensional space. For any given line, we measure how well it represents the data by computing total reconstruction error. For each data point, we first project it onto the line. The projection of a point onto the line is obtained by taking the dot product between the point and the direction of the line, and then multiplying the scalar with the direction vector. The reconstruction error for that point is the squared length of the difference between the original point and its projection. We then sum this squared error over all data points, or equivalently take the average. We also assume that the direction vector representing the line has unit length, meaning it lies on the unit sphere. Now we expand this error expression. After expansion and simplification, a constant term appears that does not depend on the direction of the line. Since this constant does not affect which line is optimal, we ignore it. What remains is a term involving the square of the dot product between each data point and the direction vector. So the problem becomes, find the unit direction vector that maximizes the average square dot product between the data points and that direction. Now we rewrite this expression in matrix form. The square dot product between a data point and the direction vector can be rewritten as the direction vector multiplied on both sides of a matrix formed by the outer product of the data point with itself. So the full objective becomes maximize the direction vector multiplied on the left and right by the average of these outer product matrices across all data points. Now we define a matrix constructed from the dataset as the average of these outer products. This matrix is a D by D matrix built entirely from the data. It captures how the data varies in different directions. This matrix is known as the covariance structure of the dataset, up to centering, which will be discussed later. Now the optimization problem becomes: find the unit vector that maximizes the direction vector multiplied on both sides by this covariance matrix. This is a standard problem in linear algebra, and the solution is well known. The optimal direction is the eigenvector corresponding to the largest eigenvalue of this matrix. So the best line that minimizes reconstruction error is given by the principal eigenvector of the data covariance structure. We will later understand covariance in more detail, but the key idea is this: finding the best compression direction in data reduces to finding the dominant eigenvector of a matrix built from the dataset.
Even if we assume that we can solve the previous optimization problem, a more important question remains: are we actually done? Let us take a step back and recall what we were trying to do. We started with a dataset, and we wanted to find a way to represent data points using proxies on a line. The idea was that once we have a line, we can project each data point onto it, store a representative direction, and then store one coefficient per data point. This gives us compression. Now we also showed that we can find the best such line by solving an optimization problem. And it turns out that the solution to that optimization problem is an eigenvector of a matrix associated with a dataset, called the covariance matrix. But for now, that is just a technical detail. Let us treat this solution as a black box. You give the dataset this black box, and it outputs a line. Now the question is, are we satisfied with this approach? Is this always the right kind of compression? To explore this, let us think more carefully. Imagine we move from 2 dimensions to 3 dimensions. Now we have a data set of points in 3-dimensional space. But instead of being scattered everywhere, the points actually lie close to a plane. So the true structure of the data is 2-dimensional, even though the ambient space is 3-dimensional. Now our method still tries to find a line that best represents the data. So it finds a single best line in this 3-dimensional space. That line will lie inside the plane, because any line outside the plane would clearly give worse reconstruction error. So the optimal line is constrained to the plane. But now here is the key issue. We are forcing all data to be represented along a single line. So every point is projected onto that line, and we get proxies along it. Now the question is this a good representation of the data? Yes, it does compress the data. But does it capture the true structure of the data set? Not necessarily, because the real structure is a plane, not a line. So what we are calling error in our model may not actually be error. It may contain real information about the data. In other words, we're throwing away structure that is actually meaningful. So our assumption that data lives near a single line is too restrictive. Now let us look at the geometry of this situation. We take each data point and project it onto the best fit line. The difference between the original point and its projection is what we previously called the error or residue. Now here is the surprising observation. These residue vectors are not random. They themselves show structure. If you plot all these residue vectors in 3-dimensional space, you will see that they tend to align in a common direction. So even the errors lie along a line. This suggests something important. The information is not exhausted after finding one line. There is still structure left in the residuals. So instead of stopping after one step, we can continue. Here is one possible procedure. First, start with the original dataset in d-dimensional space. Then find the best line for the dataset using the method we already developed. Call this first direction W1. Now project all data points onto this line and compute the residuals. Each residual is the original point minus its projection onto W1. Now we create a new dataset consisting only of these residuals. Then we repeat the same procedure on this new dataset. We find a second best line for the residual data, which we can call W2. We can continue this process again and again. Each time, we extract a direction that captures structure not explained by previous directions. In principle, we can continue this up to the dimensionality of the space. So we build a sequence of directions, each explaining remaining structure in the data. Now this raises several important questions. First, how do we reconstruct the original data once we have multiple directions? Second, what exactly does compression mean in this new setting? Third, how many such directions should we compute? And fourth, where is the compression actually happening in this multi-step process? But before answering these, there is another important issue. So far, we have assumed that we find lines passing through the origin. This assumption can fail in practice, because real data is often not centered around the origin. For example, even in 2 dimensions, data may be shifted away from the origin. In such cases, forcing a line through the origin can lead to poor representations. We might end up choosing a line that does not reflect the true direction of the data, simply because it passes through the origin. To fix this, we first need to center the data. This is done by computing the mean of the dataset, which is the average of all data points. Then we subtract this mean from every data point. This shifts the dataset so that its center is at the origin. After centering, lines through the origin become meaningful again, because the origin now represents the center of the data. So centering ensures that we are finding directions that reflect how the data is spread. Now, even after centering, several questions remain unresolved. First, how exactly do we solve the optimization problem involving the covariance structure? Second, how many times should we repeat the residual extraction process? Third, where exactly is compression happening in this iterative procedure? And fourth, what is the final representation we are actually learning? These questions will lead us toward a deeper understanding of the method. In fact, once we answer them carefully, we arrive at a powerful algorithm in data science. This becomes the first major representation learning algorithm in unsupervised learning. We will build it step by step in the next part.
Hello and welcome back. So, in this video we continue our discussion of the new algorithm we're developing for unsupervised learning, where the goal was to find a line such that, given a dataset, it minimizes the total reconstruction error from projecting points onto the line. But when we started doing that, several questions came up. First, we began with an error minimization problem, and then wrote it as an equivalent maximization problem involving a certain objective function. We want to understand that transformation more deeply. Second, we proposed a possible iterative algorithm where we keep finding multiple lines one after another. This raised the question, how many rounds of this procedure should we actually run, and when should we stop? And more fundamentally, we asked, where is compression actually happening, and what exactly are the representations we are learning? In this video, we will try to answer these questions so that the algorithm becomes more solid and well understood. We start from where we left off. We have a dataset consisting of data points x1, x2, up to xn, each lying in d-dimensional space. We defined a matrix C, which is the average overall data points of the outer product of each point with itself. In other words, for each data point, we take the vector xi, multiply it by its transpose, and then average these matrices over all data points. We then found a vector w1 that maximizes the quantity w transpose cw, subject to the constraint that the length of w is 1. This vector w1 gives us the best first direction for representing the data. Next, we construct a new dataset made of residuals. For each data point xi, we compute its projection onto w1. This projection is given by the scalar product of xi with w1, multiplied back by w1 itself. We then subtract this projection from xi. This gives us the residual vector for each data point. So each new point in this transformed dataset is original point minus its projection onto w1. Now we repeat the same idea. We compute a new matrix C', which is the average of outer products of these residual vectors with themselves. Then we find a new direction w2 that maximizes w transpose C'W, again under the condition that w is unit length.
Now an important question arises. What is the relationship between W1 and W2? Geometrically, if we look at the situation, all residual vectors are perpendicular to W1. This happens because projection removes exactly the component along W1. So the residuals lie in a direction orthogonal to W1. Therefore, when we compute the best line for these residuals, we obtain W2, which must also lie in a direction orthogonal to W1. So W1 and W2 are perpendicular. If we continue this process, we keep generating new directions W1, W2, up to WD. Each new vector is orthogonal to all previous ones, and each has unit length. So we end up with a set of orthonormal vectors. Now we can interpret what is happening with the data. Each original data point xi can be written as a sum of projections onto these directions. That is, xi equals its projection onto W1 plus its projection onto W2 plus all the way up to its projection onto WD. Each projection is obtained by taking the dot product of xi with wk and multiplying by wk. Now consider what happens after d rounds. After d rounds in d-dimensional space, the residual becomes exactly 0. This means every data point can be reconstructed perfectly as a sum of its projections onto these orthonormal directions. So what we've done is express the data in a new basis instead of standard coordinate axes. We now represent everything using the basis formed by W1 through WD. Now the key question, what have we gained? First, if the data actually lies in a lower dimensional subspace, then we do not need to run all d rounds. The residual will become 0 much earlier. This means the intrinsic dimension of the data is smaller than d. For example, suppose that after 3 rounds, all residuals become 0. Then every data point can be written using only 3 directions, W1, W2, and W3. Instead of storing d numbers per data point, we only need 3 coefficients per point, given by the dot products with these 3 vectors. So compression is achieved by storing only these coefficients, plus the 3 direction vectors themselves. In total, instead of storing d times n numbers, we store k times d numbers for the k directions, plus k times n numbers for the coefficients, where k is the number of meaningful directions found. If k is much smaller than d, this is a huge reduction in storage. Now in practice, residuals may not become exactly 0. Instead, the data may only approximately lie in a lower dimensional structure. So we allow some error tolerance. To decide how many directions to keep, we use a simple idea based on energy or variance. We observe how much each direction contributes as we go through the iterations. At first, the first direction captures the most structure. Then the second captures less, and so on. Eventually, the contribution becomes very small. At that point, we can stop. A practical rule is to choose k such that the first k directions explain a large fraction of the total variation, for example 95%. After that, remaining directions are treated as noise or negligible information. So overall, the algorithm is, we start with the data, optionally center it, then repeatedly find best directions, subtract projections, and continue until the remaining structure is small enough. At that point, we stop because additional directions do not add meaningful information. That completes the idea of how compression, representation, and structure discovery all emerge from this iterative projection process.
Here's the same explanation written in a way that can be read smoothly as audio, with equations spoken as words rather than symbols. This whole method is basically principal component analysis, and it can be understood in 3 equivalent ways: geometry, statistics, and linear algebra. All 3 are describing the same structure from different angles. First idea, variance maximization. We're trying to find a direction, called W, that has unit length such that when we project all data points onto this direction, the variance of those projected values is as large as possible. The quantity being maximized is what you can think of as W transpose times C times W, where C is the covariance matrix of the data. In words, C is just the average outer product of data points with themselves, after centering the data. The important result is the direction that maximizes this variance is the eigenvector of C corresponding to the largest eigenvalue. So the best direction is the top eigenvector. Second idea, why eigenvalues and eigenvectors appear. If you apply the covariance matrix C to its eigenvector W, the result is just a scaled version of W. That scaling factor is called the eigenvalue. So in words, eigenvectors give directions in space. Eigenvalues tell you how much variance lies in those directions, so each eigenvalue is literally the amount of spread of the data along its eigenvector direction. Third idea, the iterative algorithm you saw. You start with data points. Step 1, find the direction that captures the most variance. That is your first principal direction. Then you remove the part of each data point that lies along this direction. This leaves behind residual vectors, which are the leftover components not explained by the first direction. Step 2, you repeat the same process on the residual data. You find the next direction that captures the most variance in the residuals. Then again subtract projections. You continue this process. Now a key geometric fact happens. After the first step, all residual vectors lie in a space that is perpendicular to the first direction. After the second step, the remaining residuals lie in a space perpendicular to both first and second directions. And so on. So each new direction you find is automatically orthogonal to all previous directions. This is why you end up with an orthonormal set of directions. If you continue this process in a space of dimension d, after d steps there is nothing left. Every data point can now be written exactly as a sum of projections onto these d directions. So you have completely re-expressed the data in a new coordinate system. Instead of using the original coordinate axis, you are now using the principal component axis. Now the key interpretation. This is just a change of basis. You are writing every data point in terms of new axes that are ordered by importance. The first axis captures the most variance. The second captures the next most variance, independent of the first, and so on. Fourth idea, variance as information. When you project data onto a direction, you get a set of numbers. If those numbers have high variance, it means data points are well spread out, so they are distinguishable. If variance is low, all points collapse together and you lose information. So good directions are the ones that preserve spread. That is why PCA maximizes variance. It preserves as much information as possible under compression. Fifth idea, eigenvalues as information measure. Each eigenvalue corresponds to how much variance is captured along its eigenvector. If you sort eigenvalues from largest to smallest, the top few usually contain most of the total variance. So a common rule is keep enough top components so that their eigenvalues sum to about 95% of the total sum of all eigenvalues. This is why PCA can reduce dimensionality. Sixth idea, geometric intuition with rotation. When you switch from original axis to principal component axis, you are effectively rotating the coordinate system. In a good case like height and weight, the first principal direction aligns with the direction where both increase together. The second direction is perpendicular and captures the leftover variation. After rotation, one axis captures most structure, and the other becomes almost independent noise. So PC is also a decorrelation method. It makes features independent in a linear sense. Final summary. PCA finds new coordinate axes such that first axis captures maximum variance, each next axis captures remaining variance, while staying perpendicular to previous ones. The data becomes easy to compress and interpret. It is simultaneously variance maximization, eigendecomposition of covariance, sequential orthogonal projection and reconstruction, coordinate rotation into decorrelated features. That is the whole idea in different guises.
Here is the same explanation written in *** audio-friendly form ***. with all equations spoken naturally and no symbols. This notebook demonstrates principal component analysis using a simple numerical example. Step 1. What PCA does? The procedure has 4 main steps. First, you center the data. This means you subtract the mean from every data point so that the dataset is centered around 0. Second, you compute the covariance matrix of the centered data. This matrix captures how each feature varies with every other feature. Third, you compute eigenvalues and eigenvectors of this covariance matrix. Fourth, you sort the eigenvalues in descending order. Pick the top k eigenvectors and project the data onto them. This gives a lower dimensional representation of the data. Step 2. Centering the dataset. The dataset contains 8 points, each with 2 features. Initially, if you plot them, they are not centered. So you compute the mean of each feature and subtract it from every point. For example, a point like 4,2 becomes something like 1.25, 0.75 after centering. After doing this for all points, the dataset becomes centered around the origin. Step 3. Covariance matrix. Now you compute the covariance matrix. You take the centered data matrix, multiply it by its transpose, and divide by the number of data points. This gives a 2 by 2 matrix in this example. This matrix captures the spread and correlation structure of the data. Step 4. Eigenvalues and eigenvectors. Next, you compute eigenvalues and eigenvectors of the covariance matrix. You typically use a numerical solver for this. The largest eigenvalue in this example is about 17.5. The eigenvector associated with this largest eigenvalue gives the first principal component. This direction is the one along which the data has maximum variance. Step 5. Second principal component. The second principal component must be perpendicular to the first one. This is because after removing the variation explained by the first component, the remaining variation lies in a direction orthogonal to it. So PCA naturally produces orthogonal directions. Step 6. Choosing number of components. To decide how many components to keep, you use explained variance. You take the sum of the top k eigenvalues and divide it by the sum of all eigenvalues. This gives the fraction of variance explained by the first k components. For example, if k equals 1, you might get about 0.979. This means the first component alone explains about 97% of the total variance. So keeping just one dimension already preserves most information. Step 7. Reconstruction. Now you project the data onto the principal components. This gives you coordinates in the new space. To reconstruct the original data, you multiply these coordinates back by the eigenvectors and sum them. If you use all components, you recover the original data set exactly. If you use only the first component, you get an approximation. Step 8. Reconstruction error. To measure how good the approximation is, you compute reconstruction error. For each point, you take the original point and subtract its reconstructed version. Then you square the difference and average over all points. When projecting onto the first principal component, the error is small, about 0.375 on average. When projecting onto a random direction like the vertical axis, the error is much larger, around 8.9. This shows the PCA finds the optimal direction for minimizing reconstruction error. Step 9. Orthogonality. Check to verify if a vector can be a second principal component. You check if it is perpendicular to the first one. You do this by taking their dot product. If the dot product is 0, they are orthogonal, so the candidate is valid. Step 10. Python implementation in code. You first import numerical and plotting libraries. Then load the dataset and visualize it. Next, center the data by subtracting the mean. Then compute the covariance matrix using matrix multiplication. After that, compute eigenvalues and eigenvectors using a built-in solver. Then reconstruct the data using different numbers of components. Finally, compare reconstruction errors for different projections. Step 11. Real dataset example. Finally, PC is applied to image data, such as handwritten digits. Each image is treated as a high-dimensional vector. You compute principal components of this image dataset. Then you reconstruct images using different numbers of components. As you increase the number of components, the reconstructed image becomes closer to the original. This shows that PC can compress images while preserving structure. Funnel idea principal component analysis is essentially find directions of maximum variance rotate the coordinate system into those directions keep only the most important axes reconstruct approximately from fewer dimensions. It is a method for compression, denoising, and finding structure in data.